she'll talk about quasi-polynomial Frege simulation of CIT beyond noncommutative.
Thank you for organizing this and also giving me the opportunity to speak here. So yeah, I'm from Naizar, Bhubaneswar. We are a small group in it's an established science institute, but the CS department is quite small. But we are looking to hire actively. So if you or any of you know people who want to apply for faculty positions back in India, please think of us. Okay, so that being said, I'll be talking about Frege simulation of some PIT exams. That's to us the most interesting, but yeah, I'll get to what each of these mean. And this is joint work with Abranil, who is at IIT Kharagpur currently, and Grochow and Pitassi, who are at CMI. Okay, so, and also I am very new at this algebraic proof complexity, so if I make mistakes, please, I would be happy to be corrected. So what is the main question that we want to study in proof complexity is, like, it's an approach to trying to solve the P versus NP question. And the question is whether NP versus co-NP, they want to relate, show a separation between those two classes. So in particular, what you would want to ask is unset, the language unset, in NP? That is, if you are given a set of unsatisfiable clauses, is there a short proof of unsatisfiability? Okay, right? Which is also easily verifiable. And so now what do you mean by proof? So for that you need to define proof systems, which are essentially like a bunch of axioms, which again to me they are like the universal truths. And then there are rules which you are allowed to use to go from one line to the next. Right? And of course these proof systems must be sound and complete. So you shouldn't be able to prove false statements and all true statements you would want to prove in this system. Right? So the like one of the important questions in this area is to understand the power of so Frege proof systems, which we have already seen in the talk of Kilian and Susanna. So this is one of the first or most important proof systems, and it's we want to understand the power of this system. So now again, thanks to the brilliant introductory lecture, we know that the question was, can we use or can algebra help in this question, in trying to understand the power of Frege? And so for that, what you would want to do is firstly arithmetize the clauses themselves, right? So the way you would do it is that, so you are given a CNF, right, instance, which is AND of clauses. So what you want, so if it's unset, what you want to say is that there is no assignment which is going to satisfy all the clauses at the same time. Okay? So the way we are going to do it is, so if it's the literal xi, we will the polynomial representation of it would be 1 minus yi, like x, yeah, so y are like the algebraic variables. Okay. And for the negation xi literal, we would put it as y, just yi, right? So what we are doing is, if xi is 1, then the polynomial becomes 0, and if the Boolean variable, the satisfying thing is 0, then we want it as well. Okay. And now how do you, so for a clause it's like OR of literals, so what we are going to do is we are just going to take the product of the polynomial versions. And now what you see is that if a Boolean assignment is going to satisfy a clause, then an assignment satisfies the clause if and only if the corresponding polynomial is 0 at evaluated at that assignment, right? So now, therefore, what you get is that the Boolean function is unsatisfiable if and only if there is no common root for this system of polynomial equations, right? And as again we've seen, this is where Hilbert-Nullstellensatz comes up, and we know that if this happens to be the case, then so we are now increasing the field. And now what we have is that if there is no common root, then there must be some form of this type that must be satisfied. And yeah, so that's where the Hilbert-Nullstellensatz proof system comes in. And yeah, it was, again, as we have seen, degree bounds here lead to like propositional lower bounds there. And another measure that is studied is the sparsity of these GIs. Okay? And then one step further, if we go, Grochow and Pitassi defined the ideal proof system, where instead of like this form of the proof, what we allow is a polynomial. So so a polynomial P is the proof, and it should have the property that if you substitute, so these are like the placeholder variables, and if you substitute 0 there, then it should evaluate to 0. But if you substitute the original set of polynomials which are supposed to be not have common roots, if you substitute that, then it should be 1, right? So if there was some common root, then this could never happen. So this is like and now the measure that we are looking at is the circuit complexity of this proof polynomial. Okay, so now so IPS and PIT is actually very strongly related. Okay, so because again this is something we've seen, sorry for repetition, but so the thing is that you want proofs which are verifiable, right? So now for the IPS system, the verifiability is like you want these two equalities to hold, right? So once you plug in zeros, it should be 0, and if you plug in these f's, it should be 1. So both of these are essentially instances of the PIT question. Okay, so unfortunately, we don't know efficient PIT algorithms in general, but we do know efficient randomized algorithms. Okay, and basically what Grochow and Pitassi in the same paper that introduced IPS, what they said is that this is fine, and so they defined some PIT axioms which are basically like some tautologies that for PIT that are true, the statements which always hold about PIT. So so they defined some PIT axioms which are some tautologies, and they said that if the PIT axioms for the proof polynomial can be written in Frege, then Frege is polynomially equivalent to IPS over F2. So yeah, this is like okay. However, it's unclear how to do that. Okay. And so in the first instance where this was we were able to do this, when this was done, is in the non-commutative setting. Okay, so Lee, Ido and Wang, they showed that non-commutative IPS is actually like unconditionally, they showed it is quasi-polynomially equivalent to Frege over F2. I missed that. Okay. Right. And one of the key things there was basically that if you can show a polynomial size Frege proof of so this is what you would want to do, like you want to say that there is a polynomial size Frege proof of the negation of the unsat thing, and that you can do assuming basically the Boolean versions of these two have polynomial size Frege. Again, I will at this point maybe it's unclear. I will say what this means. But so again, as you see, the PIT is like inherently there if you want to study IPS, and especially Frege simulations of IPS. So what is non-commutative IPS? So you have a field and you have a set of variables, non-commuting variables, and you have a set of polynomial equations which don't have any common roots over 0, 1. So yeah. Okay, so therefore what you do is, actually you have a set of polynomials which don't have common roots, but you want them to not have common roots over the 0, 1 hypercube. So that's why you include the Boolean axioms. So these are like the Boolean axioms. Anything over 0, 1 will satisfy this. And these are the commuting axioms. So because you're in the non-commutative regime, you need to add these as well. So non-commutative IPS refutation is again the proof polynomial is now a non-commutative polynomial f, which has the two properties that we have seen. And now what you want to study is the size of the smallest formula which is computing this proof polynomial. Okay. So what they showed is that if you have a CNF and so Q1 through the Qi's are the corresponding polynomials for the clauses, then if there is a IPS refutation of size S for those polynomials, then there is also a Frege proof of quasi-polynomial size for the tautological negation of phi. Okay. Okay, so just what are these Q's? So the Q's now you have to think of them as, non-commuting formulas, so that like when you plug them in, they are also non-commutative. So for xi it will become, this is same as what we were doing, so xi becomes 1 minus this, negation xi becomes as is, maybe it should have kept twice, and this is again same as what we did, except that now you're thinking of them as fan into formulas, fan into non-commutative formula. Okay. Cool. So what we do is that, so we know that Frege can simulate non-commutative IPS with some quasi-poly blow up, but it is unclear if the same thing holds for the commutative case. So what one of the motivations was that what if can Frege simulate if we bring in some commutativity? So not the full commutative case, but like if we bring in a bit of commutativity, can it simulate it efficiently? So that's how, so now I will define what are partially commutative the polynomials. Okay.
It should be noted that if Frege simulate commutative IPS, then
VP is not equal. Is that sorry?
No, then PIT is in NP.
Oh yes. I should mention that.
So it's not really feasible.
Yeah. Yes, I should have. Okay. Okay. So what are partially commutative polynomials? So again, you have a field and you have now. So I'm defining it over. Okay. Let me say. So there's a field, and for now, let's say there are two buckets, two sets of variables x and y. Without loss, they have the same number of variables, but not necessary. And now a monomial is a partially commutative monomial if it is uniquely determined by its projection onto the two buckets. So what I mean is like, so basically something, something like x1, y1, x2, y2. So x is x1, x2 is coming from x and y1, y2 is coming from y. Okay, so the thing is, within a bucket, the variables don't commute, but across buckets they commute. Okay, so the x1, x2 should be as x1, x2. The y1, y2 should be as y1, y2. But this monomial is the same as, let's say, x1, y1, y2, x2. Okay, so that's what it means.
What is the liquid term?
So basically, there's a relation that comes. So these two are like there's an equivalence relation which comes in. That's what I mean. So as in these two monomials are the same because restricted to x and restricted to y, they give you the same two monomials. So so for both these monomials, mx and my are the same. That's okay. So and from that, what you get is so in general, like people have studied in various contexts. So you can think of a commutating graph, right? So the objects are in general these are from semi-rings. So in our case, it's like the variables are the vertices, and you have an edge if the pair of variables don't commute. And the two bucket case is essentially when the commuting graph is a union of two cliques. Okay, so everything within the buckets don't commute, but across the buckets they commute. Okay, and a partially commutative polynomial is an F linear combination of such monomials. And similarly, this is for two buckets, you can define it for k buckets. So now for partially commutative IPS, I mean it's essentially the same. Your variable set is now divided into k buckets, let's say, and without loss, each of the buckets have the same number of monomials variables, and you have a system of equations where again you have the Boolean axioms, that is for everything, and you have the commuting axioms for variables within a bucket. So xi is from the same bucket, two variables, because they are non-commuting, you have to add the commuting axioms. And so now refutation is again a polynomial such that if you plug in 0, it should be 0, and if you plug in the original things, it should be 1. Okay, yeah, and just because partially commutative, so there are some extra things that we need to add.
So when k is 1, it's completely non-commutative?
Yes, exactly. So the thing is that this generalizes both the as I think it's there on the next slide. Yeah, so this generalizes both the extreme cases. So when k is equal to 1, it is the non-commutative case, and if n is equal to 1, you get the commutative case. Okay. So so now the size is the minimal, the size of the smallest partially commutative formula computing this polynomial. And so our main result is basically because we defined a new sort of IPS thing, we have to just make sure that the basic things work. So this firstly generalizes both, as I already said, that the soundness, completeness, these are not anything deep, it is just work. The previous proofs just work. And yeah, so interestingly, the verifiability, the thing is because of recent work by Arvind, Abranil and Pato, we know that this case is actually deterministically verifiable if k is constant, but their proof works only over characteristic 0 fields. When the number of buckets is 2, it works over any field. But yeah, so I will come to that. But I will come to this later. Yeah, so over characteristic 2, which is our main result, over 2 buckets, which is our main result, we actually do have deterministic verifiability. Okay, so this is our main result. If we have a CNF formula over 2 buckets, it should have been x1, x2 anyway. So if it's a CNF over and the variable is divided into 2 buckets, then okay, then if you have a PC2 IPS refutation of small size, then there is also a Frege proof for the unsatisfiability of quasi-polysize. Yeah, S to the polynomial. Okay. Okay. So with, I have some time left. Okay. Yeah. So in the remaining 5 minutes or so, I will give a quick overview of how this is we do it. The overall proof strategy really is similar to the one by LTW. So there are some steps which actually sort of, these are not very hard to make it work for the partially commutative case as well. So there's a Booleanization step, okay, where you are given a non-commutative. So in the LTW case, you are given a non-commutative formula. You have to look at the Boolean version of it, and this is again not very hard to do for us. We do it. Then there is the reflection principle, which I spoke about earlier. So if you want to prove the unsatisfiability of something, then you have to essentially what have I written? Yeah, so basically if you want to prove the unsat of the whole CNF thing, it boils down to writing in Frege the correctness of some PIT. I will come to that. Yeah, sorry, but so there were basically these 3 steps which were there in LTW, and these were not very hard for us to convert to even the partially commutative setting. The main thing was this. So if there is a so what they do is that, as I had said, there basically comes down to 2 PIT axioms that you want to prove right? Yeah, and you want to prove the correctness of that PIT in Frege. If you are able to do that, then you get a Frege proof of the original IPS, the IPS refutation. Okay. So this is the main main technical contribution of LTW. And the way they do that is by the main thing is that they can write a Frege proof of the correctness of the Rasch-Pilka PIT. Okay, that is their main technical contribution. And so what was the key idea in that PIT algorithm is that, so in PIT the thing is you want to keep track of a proof of non-zero-ness, right? So you want to, if the starting polynomial that you had was non-zero, you want to make sure that you have a short certificate of maintain that the polynomial is non-zero. And okay, so that's what in general PIT is, right? So in Rasch-Pilka, what they did is they looked at if the polynomial being computed by the non-commutative formula is non-zero, then what they did was they inductively kept track of the coefficient space, but kept track of it while maintaining the size to be small. And the way they did that is, so you want to keep track of the full coefficient space, but it is enough to keep track of the basis of the coefficient space, and that is small if the formula being used to compute it is small, and therefore it could be done. Okay. So now in the proof complexity setting, instead of keeping track of in PIT you want to maintain non-zero-ness. When you write in the proof complexity setting, you want to keep track of zero-ness. Okay, so if something is being whatever is being computed is 0, then you want to make sure that you can check inductively at every step that the zero-ness is maintained. And therefore, instead of keeping track of the coefficient space, what LTW do is they keep track of the kernel of the coefficient space, and using the same idea as in Rasch-Pilka, they keep maintaining the basis of this of the kernel. Okay? So that's what I understand of this of what LTW do. And we also want to do something similar, except that so the key idea is to keep track of the basis of whatever space you want. But the way it is done in LTW or in the non-commutative setting is that you can find the basis using some sort of Gaussian elimination. Okay. Now that is fine for them because the vector spaces is over the field, like the base field. However, in our case, because we are in the partially commutative setting, these vectors are no longer over the base field but over some much more complicated object called free skew fields, which is a field which contains non-commutative, the non-commutative ring. Okay? And therefore, if you try to do Gaussian elimination over this, then you firstly have nested inverses, and the complexity of computing these become exponential. Okay? Which is why you can't like directly use that idea. Okay? And yeah, so basically you don't know how to do this in Frege. So what we therefore had to do is you want to do the same thing. You want to keep track of a short witness of zeroness, which is the basis of that. But instead of basis, what you do is you want, so these witness matrices have to be built using tools of this skew field theory, which was like developed, most of it was basically by Kohn. And using tools from skew field theory, what we can do is instead of using Gaussian elimination, we have an alternate witness matrix where each entry of these matrices are now polynomials instead of rational expressions over non-commutative polynomials. These are actually non-commutative polynomials, and therefore these can be written in Frege. Okay. So yeah, so that's our main thing. And yeah, so what these witnesses are doing are essentially they are encoding the linear dependencies, which is same as the basis change thing, but we can't do Gaussian elimination and keep the basis change matrix. They are instead, you have to do it in a different way. That's all. Okay. Yeah. That is so because of this, yeah, maybe I should mention that because we couldn't. So okay, this is about why we couldn't do LTW directly. I mentioned on the other paper by Arvind, Abranil and Partho as well. So they also give a PIT algorithm, but again we were not able to write that in Frege either. So LTW is like they took the Raspilka algorithm and made it work and write it in Frege. Even though we had a PIT algorithm with us, we couldn't write it in Frege directly because of the same reason that I was saying. So in SEM 24 basically, because in any PIT thing you are keeping track of non-zeroness versus we need proofs for zeroness, and it wasn't clear to us how to do this switch. We were able to do this only for like the 2 bucket case with a lot of work. So yeah, so therefore basically as a corollary we were in fact able to give a new PIT algorithm for the 2 bucket case. So we had to come up with a new PIT algorithm for it, which we could write as in Frege. Okay, that's sort of all I wanted to say. So in conclusion, yeah, we wanted to understand, overall we want to understand the NP versus co-NP question, and like, can algebra help in it? So yeah, you want to understand Frege, and you want to understand if Frege can simulate IPS. It's unclear in the general setting. In the non-commutative setting we knew. So the question was, what if we introduce a bit of commutativity? And the question basically boils down to checking certain identities which which we were able to do for 2 buckets. As I was saying, so efficient PIT was known, but we didn't know how to do it in Frege. And the main question is like, can we increase the 2 bucket to constant number of buckets? Because that's the regime where efficient PIT is known, but currently we don't know how to write it in Frege. So, and something which it is interesting to us, I don't know how interesting it is in general, is that maybe not Frege, but like what is the simplest or reasonable model where those PIT things, or in which this constant case can be written. Okay, thank you.
Questions? Here.
Question about the last slide. So HCM, Arvind and R, they work over zero characteristic only?
Yes.
So how did you succeed to simulate it?
No, we didn't. That's what.
Oh, you did.
We don't. Yeah, we have to come up with a new PIT, and So it's not a simulation of it.
And another quick question. In MTW there was this quasi-polynomial simulation because of homogenization.
Homogenization, same
And this
thing.
stays here.
Yes, because we also do the homogenization step.
Okay, thank you.
So, if I understand, the quasi-polynomial block is due to the homogenization step, and can you say a little bit why is it needed, or like what property?
So the PIT part of it needs it. I mean, the final step needs it to be homogenized. But yeah, it's a good question. We had thought of it.
Like the PIT algorithm that you get
needs homogeneous. Yes.
Let's thank Prerona.